Hi, this is Kent, and I'm here to present our work called Faster Algorithms for Rooted Connectivity in Directed Graphs. This is joint work with Chandra Chekuri. Okay, so some preliminaries. So we're interested in global connectivity, edge connectivity, first off, especially in simple directed graphs. So just directed graphs, but there's no parallel edges. And I'm sure everyone knows this, but just review to be safe. We say that a graph is strongly connected if there's a path from A to B for any pair of vertices A and B. And the goal is to remove the minimum number of edges so that the graph is no longer strongly connected. So if we delete these two edges across the middle, then we'll see that A can no longer reach B. Okay, although B can reach A, so it's only one direction we have to eliminate. And so the goal is to find the minimum number of edges that need to be deleted so that some pair is split up in that sense. And the edge connectivity is the minimum size of any of these edge cuts. Okay? So similarly, we can define a vertex cut to be a set of vertices whose removal makes G no longer strongly connected. And you have vertex connectivity and so forth. While our work does edge connectivity and vertex connectivity, for simplicity, I'm going to focus the talk on edge connectivity, making small comments about vertex connectivity here and there. So edge connectivity is a very basic problem. It has a long history and a lot of work. Let me just highlight a few things that are most pertinent to this presentation. So first of all, we can always figure out the edge connectivity by fixing some source vertex S and then trying out different choices of T and computing the max flow. So the first choice of ST, of course, this is in the strongly connected part, so we'll find that the connectivity from S to T1 is very big. But as soon as I get into T2 and I run it, then I'll find the appropriate cut. Okay, so one thing to keep in mind is that ST max flow has gotten much better recently and now only takes m plus n to the 1.5 time, where m is the number of edges, n is the number of vertices. Slightly better sometimes than enumerating all possible t is to randomly sample t. So if we, for example, in this kind of setting where the cut is fairly balanced, I have a 1 in 2 chance of sampling from the right-hand side and thus obtaining the minimum ST cut. Okay. A different approach, not based on ST max flow, is by Gabal, who gets an m times lambda algorithm, where lambda here and throughout refers to the edge connectivity of the graph. Okay. I'll talk more about in a moment. So about Gabal's algorithm. In this paper, we actually focus more primarily on rooted connectivity problem. So in rooted connectivity, you have a directed graph, but you also have a fixed root vertex denoted R. And a rooted edge cut is a set of edges that when you delete it, it makes it so that R can't reach some other vertex. So if we delete these two edges here, then all of these vertices can no longer be reached by R. So the goal in rooted connectivity is to find the minimum cardinality rooted edge cut. Yeah. So rooted connectivity is also very fundamental, especially because of Edmonds' arborescence theorem. So he showed that the following are equivalent. A, the graph has rooted connectivity K. B, you can pack K arborescences rooted at R. So directed spanning trees directed away from R and rooted at R into the graph. And it's also equivalent to packing K directionless spanning trees so that every non-root vertex is in degree exactly K. So Edmonds' arborescence theorem actually motivates Gabal's algorithm, which is based on efficiently packing directionless spanning trees into the graph. So Gabel's algorithm is actually directly for rooted connectivity. Of course, rooted connectivity easily implies global connectivity. You just pick any root arbitrarily. You find a minimum R cut in the graph. And in case R doesn't turn out to be on the source side of the minimum cut, reverse the graph and then compute the minimum R cut again. That'll cover the case where R happens to be on the sink side of the minimum cut, and so forth. Okay, so that's rooted edge connectivity. Likewise, one can define rooted vertex connectivity and rooted edge cuts and so forth. Okay, so here then are the main results of our work. First, I'll go over edge connectivity. So you're given a simple graph, no parallel edges, and a fixed root. And we showed that we gave a randomized algorithm that finds the minimum rooted cut in n squared time with high probability. This, of course, gives us an n squared global edge connectivity algorithm. So this is a particularly big improvement in dense graphs where the running time becomes nearly linear and improves upon the best existing running time, n cubed, by a whole factor of n. Okay? So, I said the graph has to be simple. In fact, the graph can be extended to small integer capacities, and you pay some overhead proportional to the largest capacity. We get some additional results for vertex connectivity. So, in particular, we get an n squared over epsilon running time for 1 plus epsilon approximate rooted and therefore global vertex connectivity. If we plug in 1 over kappa for epsilon, where kappa is the vertex, the actual connectivity value, then you'll get n squared kappa. And this will improve existing work, especially in dense graphs with moderately large kappa. Okay. So simple basic improvements, problems, and improvements. Okay. Okay, so let me explain the rooted edge connectivity algorithm. And in fact, I think I'll be able to explain the whole thing. So, okay, so what are the basic ideas? So one is to point out that sort of a bad case is when the graph is really dense and has very high connectivity. Because in the opposite case, where the graph is very sparse and has small connectivity, Gabel's running time of m times lambda is already very good. And the other is that is when the minimum cut has a very small sink component. So maybe the graph, maybe it sort of looks unbalanced, and the cut is like this, because then it's hard to sample. Because in the opposite case, if the cut was very balanced, so maybe it's more like this, and you have roughly n over 2 on each side, then it's relatively easy to sample a source vertex S here and a sink T here, and run the max flow to find the cut. Okay. And so the main new idea is what we call the rooted sparsification lemma. Okay, and it says the following. Suppose the sink component has k vertices. So in this picture, that's 4. Then we showed that the minimum cut has at most k edges. Okay. And then you can use that to reduce the graph to a much smaller one that has at most nk edges. And so that gives us a lot of new and useful algorithmic trade-offs. So if k, the number of vertices in the sink component, is very small, then when we run Gabel's algorithm, which normally took m lambda time for lambda to be about k and for nk edges, then we'll get nk squared time. On the other hand, when k, the number of vertices in the sinc component is very large, then we can take the max flow approach. So we sample n over k vertices or so, and then we run max flow, which normally would take n plus n to the 1.5, except we've also reduced the number of edges. And so we get n over k times nk plus n to the 1.5, which is n squared plus n to the 2.5 over k. All right. And now we just balance terms. So when I set nk squared is equal to n squared, right, into the particular n to the 2.5 over k, then I know k should be square root n, and we get a quadratic running time. Okay. All right. So this Rooted sparsification lets us find these trade-offs depending on k. So now let's prove this Rooted sparsification lemma. Okay. All right. So let's first look at the first part of the proof. The claim that so here's that sinc component of the minimum cut, which has at most k vertices. Here k is equal to 4. And the claim is that the minimum rooted cut has to have at most k edges. Okay. So let's call this T. This set of vertices, I'm going to call it T. And again, lambda is the number of edges. So we know that lambda is always just from counting and adding things up equal to the total in degree of T minus the number of edges that are within T. Okay. Now, each vertex, if I'm looking at the right-hand side here, it contributes at least lambda minus k minus 1 to the right-hand side, because I know that since each of these vertices themselves represents a rooted cut, the in degree is at least lambda. And on the other hand, since there's only k vertices in that component, at most k minus 1 of these edges are within T. So each vertex is contributing at least lambda minus k minus 1. So that tells us when we sum up over all the vertices, the lambda is at least k times lambda minus k times k minus 1. So when we start rearranging, that tells us that k times k minus 1 is at least k minus 1 times lambda. So either k is equal to 1 or k is greater than lambda. Okay, so either the sinc component is a singleton or k is bigger than lambda. Okay, great. So the contrapositive example might look like this then. Suppose again, I took the same example and I just drew more edges. So if T actually has more incoming edges than vertices, then the contrapositive says that T cannot be the sinc component of the minimum R cut. And indeed, we see that there's 5 edges going across here. So that's more than the number of vertices. So we know T shouldn't be the minimum cut, and indeed, any of these singletons actually gives us an R cut of size 4. Okay, so that's that. All right, so now let's look at the second part of this sparsification lemma. It says that now that I know that the minimum rooted cut has most k edges, I can reduce the number of edges in the graph substantially to nk. Okay. So again, this group is also simple. First, we claim that each vertex has in degree at most k plus lambda, which we know is at most 2k now, because the rooted cut has at most k edges. So I know that V has at most k minus 1 edges from other vertices in the component and at most lambda edges from the cut. So that gives us 2k. But okay, so now why is that useful? If a vertex V has in degree greater than or equal to k, so one of these vertices in the clique, for example, its in degree is bigger. Then I know it's not going to be in the cut, right? And so if V has in degree that's very big, okay, I know that it's not in the sync component of the cut, and that means I can actually contract V into the root. So I can take this vertex and I can contract it into R, and I can do it for all the high in degree vertices. Okay, and so the resulting graph, we won't contract anything in the sync component, but I'll eliminate all the high in degree vertices, so I only have nk edges at the end. Okay, so I get a nice, much smaller graph. Okay, so that establishes the entire connectivity algorithm. And just to recap the whole argument from beginning to end, we first kind of identified the two hard cases. One is, when the graph is very dense, it's high connectivity. Otherwise, Gabal's algorithm is very good. And the other is when the sync component is also kind of small, because then the sampling-based max flow approach is harder. It's harder to sample from the sync component. And the main new idea is this rooted sparsification lemma, which simply says that if the sync component is small, then the cut is also small, and then you can make the graph much smaller. Then that gives us these trade-offs where Gabal's algorithm on k edge cut with nk edges only takes nk squared time. Meanwhile, the sampling-based approach where I have to sample more vertices when k is smaller, but then the graph I work with is smaller, only has nk edges, and that gives me this n squared plus n to the 2.5 divided by k running time. Okay? Balancing terms, we get the n squared running time that I claimed. Okay, so that brings me to the conclusion. We get an n squared algorithm for edge connectivity. We get n squared times the value of the connectivity, so n squared kappa for vertex connectivity. Again, this argument is sort of similar to the rooted sparsification lemma, where we're doing some kind of packing argument. And we show that we can reduce the graph and so forth. The key ideas, I think, was to balance Gabal's algorithm against the random sampling approach. And then really, this is brought together by a rooted sparsification lemma, which sparsifies the graph relative to the size of the sync component. And then there's something good that you can do in between. Okay. All right. And then I want to mention that there's been a lot of follow-up work very recently. So one is that you can kind of take some ideas and get some quadratic time approximation algorithms. So you can approximate these rooted problems even with edge weights and vertex weights in n squared over epsilon squared time. A separate group showed an exact algorithm based on packing arborescences, so sort of more similar to Gabal's algorithm, can get you an m squared n plus n squared time algorithm, exact algorithm for rooted weighted edge connectivity. And if you actually take some of the ideas in the approximation paper and combine it with this exact algorithm, you actually get an even better exact algorithm that runs an n times m to the 2/3 plus n squared time for exact edge connectivity. Okay, so I think that leaves a couple open questions. So one is, can you get an n squared running time for weighted edge connectivity to match the unweighted algorithm that I just presented? And the other is, can we sort of get rid of this approximation, this n squared over epsilon, and get an n-squared exact algorithm for vertex connectivity, even in simple graphs, let alone weighted graphs. Okay, thank you.